in Petah Tikva, Israel. So I'm going to present today about coherent optical communication. We all know briefly about it, but I'm going to discuss about some detail about it. So let's start. I hope you are recording the session, right? Already.
Yes,
Okay. Okay, so this kind of course consists of three sessions. Session one was which are already done about background of communication and modulation format and transmitter for higher order modulation and so. The second session, which is today, I'm going to discuss today about the receiver, particularly what is the DSP in receiver, how it play the role. And the third session will be maybe in the future about the recent modulation techniques which came to the industry. Okay, so let's just start about today's session on receiver and DSP. But before moving to the session two, I hope everybody, or at least most of you, have gone through the session one, which was in the workday. If not, you can refer to it. So in the session two, I just briefly summarize it that we discussed that every minute in the internet require a huge amount of data traffic, which causes a huge amount of data traffic flow across the globe, and so exabyte per month required for global traffic increases exponentially. This is the graph by Cisco, which predicted like in 2030, the required data will be much more higher. And so we are going to support this data transmission through the fiber, as we know. And in the fiber, we know we have C-band and now we have also L-band. But even though we have C plus L-band, there is always a limited number of channel. And since the demand is increasing, so we need to increase the data rate per channel. So how we can increase the data rate per channel? By increasing the spectral efficiency. What does it mean actually? That we are going to transmit more and more data rate per bandwidth. So how we achieve it? Through the higher order modulation. And we discussed in the last session what are the higher order modulation. Briefly, we discussed how to describe the higher order modulation in the constellation diagram. So there are QPSK, 8-com, 16-com, etc. We all are almost familiar with this, I hope. And we also discussed in the last session that there is two different constellation possible for the higher order modulation, like star QAM. So it could be a star QAM or a square QAM. And we discussed that a square QAM is more preferable than a star QAM. And the reason is because the distance between symbols are equalized. So it performs better in terms of nonlinearity, in terms of all the noises which occurs in the optical network. So we prefer a square QAM as compared to the star QAM. And then we discuss how to generate this modulation format. We discuss about serial and parallel transmitters. And the parallel transmitter is preferable because it create less chirping. And less chirping is important for the nonlinear performance in the network. So, so far, till the last session, we discussed what are the higher order modulation format, how they can be generated. But in this session, we are going to discuss once you transmit these higher order modulation formats or your higher order coherent signals, how it get affected when it pass through the network and how the symbols in the constellation diagram affected. Then we're going to discuss briefly about how, not briefly, a little bit in detail about how these symbols or bits are recovered at the receiver end, that what different kind of way to recover pro and cons, different kind of receivers, something direct and coherent, polarization and phase diversity receiver. What are those? What is the meaning of it? Then we are going to discuss about synchronous detection, which is used in all the modern transceivers. And then we briefly also going to see how the dispersion, nonlinearity, and noises are gets cancelled. Okay, someone microphone is on, so can you please mute it? Okay, so this how these effects get corrected in the DSP, and these are the two terms we are going to discuss briefly. Again, this causes the cycle, this causes the bit error, and it's one of the most important in the DSP. How they correct it. How we are also at the end of session. Hopefully, we are able to see how the commercial transceiver like Acacia or Lumentum work in terms of the DSP, and why the DSP is so much important in modern coherent communication. So I start with the receiver. So we know that this is the very common block diagram for WDM system. We take different bit streams, modulate over different transceiver or different channel, you can say, lambda 1 to lambda n, multiplex it over and transmit it over optical network, which consists of series of spans, which is amplifier and fiber, and ROADM and etc. At the receiver, we demultiplex it get back the individual channel, and then try to demodulate it to get the original bits. If we are able to recover the original bits, so far we are good. Other way to represent the same system, we can say that by transmitting these bits in the higher order modulation, basically we are transmitting this constellation diagram. So basically this constellation for QPSK, for example, we are going to transmit through the optical network. At the receiver end, if we receive the same constellation, then we are able to decode the data, original bit stream from the constellation, and our communication is successful. But the question is, are we able to receive the same symbols or same constellation diagram what we transmitted? And the answer is not really. And why so? Because at the beginning of the transmission, actually we didn't transmit what looks like to be an ideal constellation for QPSK, because the transmitter itself has the phase and intensity noise. So it's noisy. As you can see, the symbols are noisy. And when even these noisy symbols are transmitted, when it transmitted through the optical link, dispersion, nonlinearity, and different kind of other noises from AC noise, from amplifier, the phase and intensity noise from the local oscillator from the receiver, or the short and thermal noise from photodetector, etc., all takes place into the signal, and it corrupt the signal, which causes the symbols in constellation diagram looks like this. This means the phase and intensity of the constellation are completely distorted, and sometimes it even cause complete 360-degree of phase rotation, and intensity also become very noisy. So can we recover this? If we receive this, can we recover the bits from this constellation? And answer is no, we can't, because we can't make a decision. There is no decision boundary here we can make. So only way to recover the bits from this noisy constellation is if you are able to convert back this noisy constellation to relatively pure constellation, and then from that we are able to detect, demodulate the original bits. And that's the concept of receiver. Receiver basically receive this very noisy constellation and try to recover the original symbol from the constellation and then decode it to the bit stream. That's the function of receiver. I just here briefly show you that how the what kind of noise affect how the symbols. So this is the ideal symbol which should be generated, but actually generated or transmitted symbols are these. And if there is only phase noise occur, which is not possible, both noise occur together. But if you oscillate just a phase noise, it changes the it causes the rotation of phase of the symbol. So you can see the individual symbol they get rotated. If both occur, which is usual case, your intensity also get. So in radial direction, you can see there are noises. This is case of QPSK. And if you have higher order modulation like 16 com, you have multiple level of intensity. So you see multiple concentric circles. And this is actually we receive at the receiver end. Where these noises comes from and how it behave, I mention here like what are the source. For example, intensity noise and phase noise comes from usually from the laser and amplifiers, and how it occur because it's noise. So it's random variation, random time dependent variation of either radius or in the phase rotation. Dispersion and nonlinear effect usually happen in fiber, also in some other component, but mostly these are deterministic effect, which is time dependent. The nonlinearity is kind of a semi-deterministic because it depends upon the also the bits pattern, and bits are random. The short and thermal noise again occur at the photodetector, and which is also causes the random time-dependent variation in the radius and phases. And if all this occur, it's surely going to cause the bit error if present, so we are going to remove it. So, okay, so what is the requirement for a good receiver? So first requirement is it must compensate all the distortion in the symbols. Second, at least it must demodulate most of the modulation format, or at least most commonly used modulation format. The third one is it must into the WDM channel because we use WDM, so we need to separate out each individual channel. Means that receiver should react only to the particular channel at time, so so the bit error will be lesser and lesser. Sensitivity should be higher. What is the meaning of it? That if received power is very small, still the receiver is going to demodulate the signal into the bits. So if receiver can take as much as lower power and is still able to decode to the bits, we call it like very high sensitive receiver. And in practice, we have seen that like Acacia or other transceiver, we have usually minus 10 dBm or minus 18 dBm. Till minus 18 dBm, we found is good, very low power it can detect, so it's very highly sensitive. That's good for the receiver. Next requirement is it must be low optical and electrical complex. If it is low optical and electrical complex, the cost will be very cheaper, but doesn't happen. Either one of them is complex. So these are the requirement, and what are different kind of receiver we have. We can see is direct detection receiver or coherent detection. Direct detection can demodulate mostly ASK, PSK, or star QAM, but the coherent detection detects mostly all kind of signal. Again, the coherent are two type: phase diversity receiver and synchronous detection. The phase diversity receiver was the earlier version or old version of the coherent receiver, and now we have the synchronous detection for quite a long time. So we are going to discuss all details about all of them. Before moving to the how this receiver work, I'm just going to introduce some essential component which is used in these receivers. So one of them is delay line interferometer. What it is, we are going to discuss now. So you know that how to detect the optical signal. So at the end, we need to convert it to the electrical signal or electrical current, and for that purpose, we use photodetector. Now, a photodetector can convert the optical power to the electrical power with this equation. We know about it. So if there is a variation in the amplitude, for example, if you have an OK signal, we just put to the photodetector and we get variation in the current. And so we can put a threshold and decide which one is what bit. And that's very common for OK kind of signal. But for higher order modulation, where the information lies in the phase, the simple photodetector cannot convert the phase to the current. So what we can do, we can try to convert the phase to the intensity and then provide this intensity to the photodetector, which in turn convert to current. So overall, we are able to convert the phase to the current. So we do some sort of manipulation using the optical circuitry to convert the phase directly to the current. And what we use for this kind of conversion is called interference, or we use it interferometer. The interferometer we use is called delay line interferometer. Basically, it takes the signal, delay it with the one symbol duration in one path. In other path, we provide some fixed phase reference phase to change the constellation places. And at the output, we receive this. So if you do a little bit mathematics, you can find out what is the optical power, output power of the coupler here. And at the end, we put a balance detector. The balance detector has a two-photo detector, which subtract the current between one and minus one to other. And so if you look at the balance detector output current, you can find this expression. Now, if you look at very closely the expression, you can find that the current itself is proportional to phase change, the phase difference of the signal. Means like it depend upon the phase of a signal minus the previous symbol duration phase. So it can able to detect only the differential phase, not the absolute phase. So that's the problem with the photo delay line interferometer. The next component I'm going to discuss is 2 into 4 90-degree hybrid. What it does is very similar to delay line, but it doesn't use a delay. Instead, it uses a 90-degree phase. And we provide the two input here, and the output we get 4. And if you do a little bit of mathematics, you can find out that the output here, if you put a balance detector, the two output current are in and Q phase to each other. What does it mean? That if you remember the IQ mode, how we generate the higher order modulation, we have a constellation diagram, and we use IQ modulator to generate it. And if you have a detector which can separate this I and Q component, basically of the, you are able to detect the higher order modulation, and that's what it's used for. So IQ modulator can detect I and Q component of higher order modulation, so we are good to go. So this is the reason it used in both the direct and coherent detection as well. Okay, so the next one we'll discuss about direct detection. I have to go a little bit fast because I have to cover a lot, but you can stop me and ask any question if you have. So how the direct detection work? For simplest format like OK or OSK signal, it's just a variation in the optical power. So 1 and 0 are represented by presence and absence of power, something like that. You put in the photodetector, you have the same variation in the current, you put a threshold and you're good to go. In the symbol duration, you have power, then it's 1 or not 0. And that's all. You can detect the OK very simply. But for higher order modulation, for example, if you go for 16 QAM, you have variation in intensity and the phase. But in this case of which is a star QAM, the phase are symmetrical. The intensity has two level, but the phase in two intensity level are symmetrical. So what we can do, we can put a threshold for intensity. So we take a branch of the input signal, divide into two parts, and take the intensity detection branch, put it in the photon detector, and we can decide whether it's high or low intensity. So we can decode the bits or data which is responsible for the intensity variation. And next we need to only do detection of the phase, either one of the path. So we take one of the intensity here, we take the here, and we try to divide into I and Q part of this constellation, and we can do it using some special kind of coupler which can provide also the phase shift of 90 degree. And then thereafter we use a delay line interferometer which can convert these phases into intensity, and then we obtain I and Q phase. So we obtain the intensity, we obtain I and Q information, so we can demodulate the data after that. Another way of doing the same thing is just feed it to the 90-degree hybrid for the phase demodulation, and still we can get I and Q part. So this is the very simplest one. It doesn't have the big circuitry, it doesn't have the big DSP or something. But the problem is it can only demodulate the differential phase or the star quam. The square quam, which is more probable in the communication, it can't demodulate because it has the various intensity level, and each intensity level phases are not symmetrical. So we can't use the direct detection for that. Another problem we face in direct detection is the receiver sensitivity. Since direct detection always require a phase reference for interference in order to convert the phase to intensity information, and the phase reference is the signal which is delayed by a symbol duration. And since your signal is noisy, so your delayed signal will also be noisy. So your phase reference is noisy, and so because of that, generated output will be extreme noisy. And so if it's more noisy, it will be less sensitive. So it won't be higher sensitive. And this is one of the problem with the direct detection. So to overcome this problem, overcome all these problems, first problem is only differential detection. Second is can't demodulate the square higher order modulation. And third one is the sensitivity is very low. We move to coherent detection. So those are very earlier era of detection of the symbols. After that, we move to coherent detection. And so coherent detection, what it does, instead of taking a reference for interference as a signal, it takes a separate local oscillator. And this local oscillator is less noisy because it's not passing through the optical network. It's a local signal, a local laser. So the sensitivity of the generated product will be very higher. So receiver sensitivity is higher in case of coherent detection. And if you do the same calculation in terms of mathematics, you reach to this equation. And you can see one interesting thing is that the current here in case of coherent detection, it doesn't have the differential phase. You can see the phase is absolute phase at that time, not phi t minus previous symbol duration phase. So this means it can detect the absolute phase. So we don't need to use the differential encoding in the transmitted signal. So one of the benefit is this one here. But all these benefits, and also we can see that later on that it can demodulate the square quam, but all of this benefit comes to certain expense. And what is the expense here we get is this delta omega terms, which is the frequency of the channel minus the frequency of local oscillator. And because this term present in the coherent detection, what will happen that your constellation is going to rotate in terms of angle, in terms of phase, and that will be the time dependent constellation. So basically we are trying to make more sensitive, but we are going to add some sort of more distortion, which is deterministic distortion. But we are going to introduce more distortion, and DSP is going to remove that. That's a part of the DSP in the coherent detection. And again, intensity and phase modulation we can convert and demodulate the signal into ASK and PSK signal in the usual way. So let's look very closer again to this equation, which is the core for coherent communication, coherent receiver. The phi AT and phi T here are the information. So all the information either in the intensity is here or in the phase is here. That's we need to recover. And we are going to add extra term because of the coherent detection, which causes the time dependent rotation. So basically this is your signals. And when it's not noisy, but because of delta omega T, it's going to be rotate the phase like this. So we are adding this rotation. Then another thing we add is the fixed phase difference between the carrier, which is our channel, and the local oscillator. Again, it's also caused some fixed rotation. Another term we add is noise term, the phase noise of the carrier itself from the transmitter in, and the local oscillator, which also causes the random time rotation of the symbols in constellation diagram. So all these three terms we add, which causes the phase error. We can put a term as a phase error, which causes an additional phase error, you can say. some sort of, and we need to remove this phase error. And how we can do it? So we need to, lucky for us that some of them are deterministic, so we can determine it in the DSP. And how we do it? By using the phase locking and carrier synchronization between the signal and the local oscillator. And that's the main aspect of the DSP in the receiver. So what is the requirement for local oscillator if you use coherent detection? So first of all, there is that it must be phase locked between carrier and local oscillator. So phase locking is essential part in order to cancel this fixed phase difference between carrier and local oscillator. So in order to cancel this rotation, we need to phase lock between carrier and local oscillator. Polarization must be aligned, which is very common requirement of any kind of interference. And then the local oscillator power itself must be much higher than the carrier power. Usually it's 20 dB higher than, in order to reduce the short noise of the photo detector. So that's another requirement. These are some differences, and I will quickly go through it, but you can refer to it later on. The most important is the sensitivity. The coherent detection is highly sensitive, so it can detect very smallest power. And another thing is, of course, it can do
Hello.
all
Hello.
kind. Yeah,
Yeah, hi, Abhishek. Sorry to
yeah.
interrupt. One small question. You were
Mm,
mentioning that in the previous slide that the for any kind of interferometry technique, we need to uh, align the phase of the carrier as well as the local oscillator. But most
mhm,
of these times we are using phase also as part of a modulation, right? So those things, how do we
mhm.
handle usually?
Okay, we will come to. So you are saying that how we do basically the phase locking between carrier and the local oscillator, right?
Yeah, because we use both the polarizations, right? So that's why I'm asking.
So there is something called polarization diversity receiver, which I'm going to discuss next. And this is one thing. And the second thing you will see later on how we do the phase locking. Okay, both of them you will see in next few slides.
Sure,
Okay.
sure. Yeah, sure.
Okay, thank you. Okay, so another benefit of the coherent receiver is we can electronically compensate dispersion and nonlinearity, which is not available in direct detection. It can demodulate most of the high order modulation format. So these are the most. You can go through all of them and see what are the differences. Okay, so now how to choose the local oscillator frequency? So the best way to choose local oscillator frequency is having the same frequency of the channel. And that way we can remove this extra phase rotation term, extra delta W terms. So that's called homodyne detection when the frequency are same. But the and it's more beneficial in terms of electrical component as well, because if you have the same frequency, the generated bandwidth, the generated current has the same bandwidth as your signal. So generated current has the same bandwidth of AT or phi t. So information bandwidth is same as electrical bandwidth, and it's good to go. But the problem is that it's very difficult to find the channel frequency and local frequency, oscillator frequency same. Because first of all, it's very difficult to find anywhere because the frequency of the local oscillator vary with the time drift. So it's very difficult to do it. Phase locking is extremely difficult, so we don't do this. So we can move to another one, which is called heterodyne detection, where the frequency of local oscillator and signal is not same. So we generate this term delta omega, which is called intermediate frequency. That's difference term. And because this difference term present, which is you can see here, this is the local oscillator of heterodyne frequency. Because of this term present, we add additional bandwidth other than signal and other than signal, and that additional bandwidth sometime two times the symbol rate or two times the actual information bandwidth. So we are going to consume extra electrical bandwidth more than the information rate in case of heterodyne detection, which is not preferable because your photo detector has the limited bandwidth, the electrical amplifier has a limited bandwidth, so we don't prefer this as well. So we go for something called intradyne detection, where we can't achieve this and we not prefer this. So we go in between. We detune the laser frequency, local oscillator frequency from the channel frequency by a small amount, so that we have a very small offset between the carrier and the local oscillator. So electrical bandwidth will be very small, so little extra than the information bandwidth. And also this term is small, so easy to compensate when we do the DSP. These are the some differences between all of three, and I'm not going through it. You can look at later on, but I mention all of them here, and some of them are very helpful. How, especially the most part we are going to discuss is carrier synchronization. So homodyne detection, they use optical phase lock loop, which is not easy to do, so we discard it. Heterodyne detection use electrical, and what we use is intradyne, which is called digital phase lock loop. We are going to discuss intradyne detection. Okay. So before we move again to intradyne, let's see some essential component in the coherent detection. Okay,
Abhishek, what is
somebody
the
asked.
advantage of intradyne here? Like, I
Okay,
mean,
so
we usually use phase lock to recover the carrier frequency, right?
phase lock is extremely difficult thing to do in optical domain,
Okay.
and I will tell you the phase lock even it's not stable for a few minutes. Sometimes very good phase locking they made is few hours. So you can't use in the
Okay.
network. You need a phase locking
Okay.
for years. Yeah. So that's why we don't use homodyne. Heterodyne, I told you why I don't use. So intradyne is always preferred. Yeah. Okay, so these are the essential component we are going to discuss. We are going to use in the coherent detection. One is called optical quadrature front end, and you can look at the diagram. It's just 2 into 4 90-degree hybrid. So we are going to generate basically I and Q component and put a photo detector, balance photo detector. So basically we are going to generate the current I and Q, which is in phase and Q phase current corresponding to I and Q of constellation diagram. So this is what we are going to use. We see how we use it. And and the second thing is is what we use is polarization diversity receiver. What polarization diversity receiver is do? First, as somebody asked just now, that the local oscillator and the signal must be aligned in terms of polarization, and how we align it. So we pass it through something called polarization beam splitter. The polarization beam splitter has a reference direction, so it converts the signal to parallel and perpendicular to the reference direction of PBS, and same for the local oscillator. So even they are not aligned in the beginning, because the polarization beam splitter is split it into two similar direction, then we combine the parallel and perpendicular direction together, and give it to the optical quadrature front end, and then we create I part and QQ part, and which combine again to finally get I and Q part of the current. And this is the way we align the polarization of local oscillator and the received signal. Okay, is it clear? And not only
Yes,
that,
yes.
this yeah, and not only that, you remember that we have two different polarization. We transmit DP dual polarization signals. So there also we use polarization diversity receiver in order to combine the, because your information is in 90-degree different polarization, right? In our all Acacia module, we transmit not transmit QPSK, we transmit dual polarization QPSK. So these two orthogonal polarization also use this setup in order to combine the bits or information into polarization in order to get detected. So this also used there as well. We can see that later on in the slides. Okay, so again, so these are the equation we are going to get from optical quadrature fronted, and this is basically the front part of the DS. So before this basically it's convert the optical signal to electrical signal, right? So your optical IQ signals it convert to electrical IQ signal, and after this we are going to use the DSP. So that's why it's called optical quadrature front end, because it's in the front of the DSP and it do the quadrature creation of I and Q. So these are the equation you can see again. And so what is the aim of our current detection is that again we need to receive A and we need to recover the information from A and phi. This is our intensity and phasor information. That's what we need to recover. But we have additional term which causes error. We call it phase error, which are these. So and also the short noises. So these causes the error. It could be noise, it could be dispersion, nonlinearity. It come from various sources, and also it come from the receiver itself. So we need to eliminate all this term, and if you are able to eliminate this, means we are good to go. We can recover the data without error. So depending upon how we remove the noise, it called two different. Even in the coherent, we have two different time depending upon how you remove this extra phase error term. One is called phase diversity deceiver, and again there is analog and digital. It doesn't require phase locking, and it was the very earlier version of the transceivers. They used very earlier version. Now we for a long time we moved to modern coherent transceivers where we use synchronous detection, where we do require phase locking. So okay, so let's start with the very simple one, the phase diversity receiver, which is analog. So we have a quadrature front end, and how to recover the data. If I need to recover the amplitude data, we have I and Q part. We just do this operation. We can do it electrical circuit. So this is electrical current now. We can use electrical circuit to do this operation, a square root operation. And if you do a square root operation, basically you get the radius part of the higher order modulation, and so we get the intensity information. So and then you use multi-level current threshold to decide whether it's 0 or 1, or what are the bit information lies in the intensity. And if you need to recover the data from the PSK, from the phase part of the signal, so what we do, we use this kind of setup. Basically, the optical quadrature frontend. Again, we use get the I and Q part of the current. Again, it's electrical, and use this circuitry. If you go through this all circuitry and try to find out what is the output equation, I and Q part, you will find this equation, I and Q. What is interesting here to see is the phi zero term, which is the phase of this channel minus the local oscillator, which was needed to do the phase locking. It doesn't present, it get cancelled because of the operation. So if it doesn't present, we don't need to create phase locking, and that's as simple as possible. But the other terms are present. So delta omega t, which is the kind of frequency offset term, this present, and also the phase noise present, and still we need to cancel it. If we have both ASK and PSK for higher order forms, so we can use this. Sorry. So we can use both of them together in a way to recover intensity and phase information. And again, we need to. So what is the critical in this in this receiver is phase noise term, which is present, and the frequency offset. And they use something called automatic frequency control. We are not going to discuss it here, but they use it to reduce the frequency offset drift, which is moving with the time. It's not very effective, so that's why this method was abandoned and not used very much. Again, here they can use only differential phase, because you can see it has the delta phi term, which is the phase of the signal minus the phase of the previous symbol duration. So it cannot detect absolute phase, it can only detect the differential phase. This is the problem here as well. And another one is it cannot detect the square quam. It takes the intensity, do the separate intensity and the phase separate, assuming that both intensity level has the symmetrical phases. So it can do this recovery. So that's why it's only used for a star quam. It can't be used for a square quam. So these are the problem with this analog version. Digital version is still the same, almost the same. It's the same thing. What you do, the same operation you do in the digital domain. Means you need to sample it, A to D converter, you sample it, and then you provide the same circuitry, and we get the very similar equation. The only benefit they get it in the digital domain is something called EDE. EDE is electronic dispersion equalization. So by using EDE, they can try to reduce the frequency offset, they can try to reduce the phase noise, and they can do other operations like reducing nonlinearity or even reducing dispersion. So that's why they moved to digital domain of the phase diversity receiver, which is better than analog, and it was used for some time. Again, it has the same problem. It cannot demodulate the differential phase, and it cannot demodulate the square quam. And again, one of the most important thing to notice here is that it used the phase reference, right? It used the delta phi, which is the phase reference of the signal itself from the previous signal duration. So it doesn't have the good sensitivity. So sensitivity is very low as well. So and after you have this intensity and phase thing converted into the electrical current, you can apply the decision circuitry. You can provide the threshold to decide where they lie, and then you can decode the data. You can go through this diagram. It's very simple. You need to provide a logic, whether it's higher intensity or lower intensity, or which phase region the current is lying, and based on that, you can decode which symbol it is. Of course, there is a lot of noise present even after this, so sometimes you miss. Sometimes you detect this one while the bits was that, so you get bit error. But at the end of all the processing, they always need to use the data recovery. So they need to convert intensity information to the intensity current, phase information to phase current, and then they need to apply the decision circuitry to get back to the bit level. Okay, so next we are going to discuss the synchronous detection, and this is used in the most of the modern coherent transceiver, the transceiver we also use. Okay, so far we have seen that both direct detection and even in terms of coherent detection with phase diversity receiver, both uses delayed version of signal as a reference. So sensitivity is very bad. It can only detect differential phase, and it cannot demodulate the square quam. And so we move to the synchronous detection, which based on the absolute phase information of local oscillator. So it's less noisy, high sensitivity again, And the most important, it can detect the absolute phase. And it's also, we see later on that it can demodulate the square comb. So we are good to go because it's going to demodulate most of the higher order modulation format. Again, it have the same quadrature fronted, what we discussed. So now if you look at the equation of the I and Q part of the this front end, optical quadrature front end, that's this and this part. And basically this representing the symbols of the constellation. So if you write the complex phasor, which is I plus JQ part, you get this equation. And this is the equation actually of the received signal, or let's say this is the equation representing the symbols in the constellation. So what if you look at it, what are these? So AT is this part, which is your information, which is either intensity information or phase information or both of them. So this is the information, this is what we need to recover. And this term, the capital phi T, is the phase error. And this phase error either coming from by the virtue of local oscillator coherent detection, or because of the noises in the signal, local oscillator, or the dispersion, nonlinearity, etc. Everything is coming here. And this kind of the another term is NC, which is the complex short noise. Either is coming from the photodetector or is coming because of the beating between local oscillator noise and AC noise. So these are the complex phase noise. It's also contribute to the phase and intensity noise. So this part, the phase error part, is responsible for rotation of the signal in the constellation. Either it can be a fixed rotation, but the time dependent rotation, like frequency offset coming because of the frequency offset term, or a random time dependent rotation because of coming out of the laser phase noises of local oscillator and the channel, or simple phase offset because of the phase locking problem. So it can come from here as well, but it's fixed, so you can easily remove. And then complex short noise, what we discussed from the photodetector, it can contribute both to the phase and intensity level. So the synchronous detection need to do what is called carrier synchronization. What is the meaning of carrier synchronization is? It try to synchronize local oscillator and carrier to compensate for all this phase error. So what is the aim of the synchronous carrier synchronization is try to find out what is the phase error. And once we find out what is the phase error, we can rotate the constellation in opposite way of the phase error, and we can recover the original signal. So basically what I'm saying is you find out what is phi t and apply here e to power minus j phi t. This term get cancelled and you have only the information, and we are good to recover the signal. So that's the basic principle of the carrier synchronization. And the way to, when we recover it, this method is called carrier recovery. Recovering the carrier or the signal from the noisy phase error and noise is called the carrier recovery. So there are two types of carrier recovery. One is optical and electronic, which is closed loop and open loop. So optical one require optical PLL, optical phase lock loop. What it does basically, so after the quadrature front end, you have the I and Q. It takes some circuitry to generate some feedback current, and the feedback current go to the laser and ask the laser to move its frequency in a way that frequency of the carrier and laser are synchronized. Also, the phase is synchronized with the carrier, and this way we can achieve the phase lock loop. And the phase lock loop is complete means you basically what we are saying that the phase of the carrier and the stage of the local oscillator is same. The noise term and the phase offset term, not the information term, and the frequency is also same. So this term basically almost reduced to zero. Not always, not exactly, but almost reduced to zero. And this is the one way of getting the carrier recovery. That's called closed loop or optical PLL. Now the problem with the optical PLL, it's very complex. It's very difficult to do. Even if you do the phase locking, it takes only few minutes or few hours, and then it come out of the phase lock. But once you are able to do that, basically the okay, basically, if you are able to do that, we are able to fix the constellation at certain point. All this rotation will go on, and basically the constellation are perfectly permanently fixed to the original place or close to original place, and that's the benefit of phase locking. Okay, but since it's very difficult to implement, so we go for open loop, which is called digital equalization, and we are going to see this one how it digitally equalize. And such receiver which use the digital equalization is called digital coherent receiver. And so we are going to estimate the phase error in digital domain through the DSP. So we call it digital phase estimation. Okay, so let's see the block diagram. So we have optical phase, optical coordinate fronted, which convert your optical information to current information in terms of I and Q of the constellation diagram, and then it followed by the DSP. So you have A to D converter, so which convert this analog signal to digital domain. And then you have different block, and every block has a different function. We are going to discuss some of them in detail and some of them very briefly. The first one is non-adaptive FDE. Is basically is try to equalize the chromatic dispersion. The timing recovery circuit basically try to recover the symbol rate or the timing. And adaptive EDE is try to correct in the frequency domain, in the time domain, both nonlinearity and the dispersion. So both these try to recover either frequency dispersion or nonlinear effect in the DSP. At the end, we have digital phase estimation. That's the way to find out delta phi, the phase error, and then we are going to correct the phase error, and then we get the I and Q, which is relatively better current in INQ part means we are get rid of the phase and intensity noise, most of it, and then we provide it to the data recovery service to recover the bits. Once it out of the noise, so you can easily recover the bits without much error. So let's see one by one. So here this is for single polarization, and again, if you have two polarization, which is the most of the case, we use polarization diversity receiver to align the both different polarization of the with respect to the local oscillator again. Okay, so here, so let's see. First, let's start
Hel-
with A to D conversion. Yeah,
Hello, Abhishek.
yeah,
Hello. Yeah, few
yeah,
questions here.
yeah.
You were
Mm.
mentioning about in the synchronous closed loop. You're mentioning that we'll try to lock the uh, carrier to the local oscillator. You're trying to lock the
Correct.
phase, right?
Yeah, phase and
Yeah,
frequency both.
present frequency. Yeah, but
Yeah.
actually, in the in what we are trying to communicate, the carrier is always varying, right? Because as we are modulating the phase of the signal as well, how I mean, how do we exactly log this? Because the phase is continuously varying the incoming signal. Does it work that fast really, phase lock loops?
Okay, so we are not locking the phase information term. So you remember this phi zero is if you phi zero term is the so when you transmit, let's say there is no information, just you are transmitting a laser. Laser always come with some fixed phase, and the local oscillator has a fixed phase. So that fixed phase difference is the this one. It can change, it can drift as well with the time, and when it drift with the time, it's called laser phase noise. That's the here. So we and then another term is delta. So we try to reduce this. We never touch with the information. If you touch with the information and try to lock with that, it won't lock. And also we play around the information, so you're not able to recover anything. And at the end, we don't use it. So it's the best way to use it because then you don't require DSP if you use, let's say if you are able to generate very good phase lock optical phase lock loop, you don't need DSP at all. You need very small DSP, and the cost of the transceiver will reduce then because your heat sink problem and everything will be solved. But the problem is we don't have the good optical PLL at all. So we basically don't use it at all. Our transceiver don't use it. We use electronic. So we recover the phase lock loop electronically. Okay.
Okay, so you're saying that whatever the carrier we are receiving, it has some phase, some
Mm.
with and the difference between this local oscillator phase and that carrier phase, we are trying to keep it. We are trying to keep that in lock. Is that what you're trying to
Yeah,
say?
exactly. Keep it fixed. It should not vary with the time, but we
So
don't
then
use
what
it.
exactly are
I
we varying if the incoming carrier is coming with some fixed phase, let's say like you mentioned, then what exactly are we trying to use if we say phase modulation? So is it a
so let me
different
clarify.
thing
Let
or
me
am I
clarify.
confused?
Let me clarify. We don't use it at all in our transceiver. This one is one of the concept. They started to build the transceiver based on it, but we don't use it at all. We don't use local oscillator at all. In that sense, we used it. We don't use the phase locking at all. We use local oscillator, but not the phase locking. We don't use the optical phase locking. What we do is this one, and I will show you what is this. This we do the phase locking in electrical domain, so we don't try to play with the phase of the laser in the optical domain at all. So we go in the digital phase estimation part, and then you will see that how we perform the same operation. What is the main idea? The main idea is to find the phase error. It doesn't matter you find electrically or you find optically. right? So you is going to see that in the DSP, how the DSP try to find the phase estimation, the phase delta phi term, the phase error term, not optically. So we use this, we don't use this at all. Okay,
Okay. Okay.
clear? Yeah, yeah.
Yeah.
Okay, okay. So let's see first A to D conversion. So this is the optical power. Let's say it's I and Q. I'm just mentioning one. It goes to the quadrature fund in, and then you generate some current, electrical current with respect to time varying like that. And then we do is sampling, and we sample it, and then we do quantization. Okay. Now, when you do sampling, we need to always be careful that we are at the transmitter in, we send the data at every symbol duration, every TS time. So we need to sample on the same interval, otherwise we lose the information. Or we oversample. If we do less than this, then we oversample it. So we must sample at the sample symbol duration of symbol duration or symbol rate. And then we do quantization, and quantization create another noise, which is called quantization noise, which are responsible for some of the bit error. We can't avoid it. It's always present. So let's see the problem with the sampling, because we need to sample at the symbol rate. And we know through the Nyquist criteria of sampling, if you sample any signal, you must follow the 2 times of the bandwidth. The sampling rate must be greater than 2 times of bandwidth. If you don't do that, you have aliasing and there is an interference here and here. So the spectrum will get distorted, at least at the end, not all the part, but at the tail, when you sample at lower than the preferred Nyquist rate. Now remember that we need to sample at the symbol duration. And what is the 1 by symbol duration is your symbol rate, and symbol rate is equivalent to the bandwidth of the signal. So the Nyquist criteria asking us to sample twice, at least minimum of twice of the bandwidth. But because of the symbol rate is asking us to sample at bandwidth. So it can cause aliasing, and how we recover it. So we use something called anti-aliasing filter. So where we have distortion, we try to chop it off with anti-aliasing filter and then sample it. And of course and then there is no aliasing. And of course, since we are chopping the signal, part of signal, so we are going to lose some information. So it's going to cause some sort of bit error. And these bit error are always present. We can see much later on that how the fake try to remove this, all the bit error which is coming out of the DSP. And not only DSP, by nonlinearity and dispersion, even if you do all the processing, still some error remain. So we can see at the end that how the fake try to act on and try to remove this bit error, residual bit error. Okay, the next part is non-adaptive FDE, and now here is some important concept, because we see in our optical network as well. So effect of chromatic dispersion. If it is just a OAK signal, intensity modulation, you can see that because of the dispersion, the pulse get broadened, and because the pulse gets broadened, some of the pulse can interfere to other duration and can cause a bit error when you apply a threshold. So here there was no pulse, but some power is present, and so it can detect as a 1. So the dispersion can cause a bit error. But for the higher order modulation, the chances are very low. First of all, the chances are anyway low because you have multiple threshold. And the second, because most of the information are in the phase. So intensity variation doesn't make much change for the bit error. So higher order modulation, the dispersion doesn't affect much. It affects, but not much. But what affect much is nonlinear effect. Nonlinear effect, we have done a separate session before, both all of these effect, what is SPM, XPM, four-way mixing, etc. And these all effect cause chirping and crosstalk between the channel. And because of this nonlinear effect, you have symbol rate error or bit error present in higher order modulation. So all these nonlinear effect cause what is called chirping. And if you look at the dispersion, this also creates chirping, but the direction is opposite to the direction of this SPM and XPM. So if both effects are present, they try to compensate each other. So chirping due to dispersion actually try to reduce the, not compensate, but to reduce the effect of nonlinearity. And this is the reason if you transmit the higher order modulation where nonlinearity play a major role, not the dispersion. So we let dispersion happen in the fiber so that the effect of nonlinearity will be reduced. And this is the reason we don't use DCF or dispersion compensating fiber in our network, at least in the for higher order modulation. With the older network XDM or something like that, where you transmit more intensity information, we use DCF. But new network, we don't use DCF in the network. And this is the reason. But still, even if you don't use DCF, so we don't compensate the dispersion, and it's good for the higher order modulation. But nonetheless, dispersion is still present, and we need to remove it, and we remove it using electronic way to reduce the beta error. And it done in the frequency and time domain equalization. So it's a very simple way to do it, at least in theoretically. It takes a lot of time to explain it, but I'm not going to discuss mathematics and all the process. You can go through here, but it's just like chromatic dispersion. We can model it as kind of a filter, and so in the frequency domain you have this filter function or the frequency filter diagram, and this filter you can implement electronically. And when the signal pass through this electrical filter, which is opposite of the dispersion, so it compensates the dispersion. And so there are many algorithms used for it to compensate the dispersion. So basically what I'm saying that we will create a filter whose filter profile is opposite to the dispersion is facing the fiber. And then that way it compensates and you reduce the dispersion in DSP. These are some of the method they use. You can go through later on. There are a lot of paper. You can go through it and see how they do it. The next one is adaptive ADE, electric domain equalization. And here, again, I'm not going to discuss much about it. I'm just going to tell you what it does. So again, it create FIR filter, but in the time domain, not the frequency domain. And there they use some algorithm to remove the dispersion, very similar to what we discussed in the past. And then it also remove nonlinear effect. And they use a lot of algorithm. One of the commonly used algorithm is called distal backpropagation. Basically, to try to propagate the signal in electrical domain in the backward way, how it faces in the fiber. So have this opposite effect of the nonlinearity of the fiber, and they compensate. There are many algorithms like this. An important thing to note that some of the Acacia transceivers support this kind of um, functionality in the DSP. And if you remember, we discussed, Eyal also discussed, and we have done some testing as well, that some of the register in the Acacia module you can enable to reduce the nonlinear effect. It doesn't compensate too much, but it can give you 0.5, 0.6 dB improvement in the OSNR, something like that. Then other things also in this domain is done. Polarization demultiplexing, polarization tracking algorithms are used. There are a lot of functionality also in the Acacia. There are function also which use this, and they give user to define it, and you can play around and the receiver in to see that OSNR is improved or not, and so forth. So this is the adaptive DD. There are a lot of algorithm, but I'm not discussing it here. Let's move quickly to the phase estimation, because the phase estimation is the phase error, and we need to compensate that phase error. So what is the how we compensate the phase error? Now, if you remember, this is the signal. We need to remove this E5 K term. Okay, right? AK is the information where information lies in intensity and the phase, and this capital phi K term is the phase error, and we need to compensate it. How we do it? So we do it in the DSP. We take a block of n symbol. We take a serial symbol with the time, convert, make it parallelized, and then we apply power of m electronically. Basically, it's a mathematical function. So we go to the power of m, where m is your higher order modulation. For 16 com is 4, for QPSK is 2, for 8 com is 3. So it goes like that. So you go to the power like that. um, uh, Sorry, the QPSK is 4 because you have 4 quadrant and so on, and at 8 com is like again 8, something like that. It goes. I will show you later on. And why we do that? Because when you go to the power of m, the phase information m multiplied over this is goes away, and what we left is m pi k, m times the phase error. And so we get finally m time phase error, and we divide by m. So we have only phi k, the actual phase error, and we take argument operation in the DSP, means calculating the angle. So we find the phase, and then we feed this phase information minus of phase information to original symbol, multiply it together. So minus phi k and plus phi k cancel each other, and we end up with the kind of error-free, phase error-free symbols in the DSP domain. It looks very sometimes very complicated, the figures and something. So I make it very simple in the constellation diagram how it's what actually done. So for example, this is your QPSK. So QPSK is represented by this in terms of the phase. This is the phase information. So in terms of the phase, let's say if there is no noise, nothing is complete pure QPSK signal. So we represent like this. So you have intensity, which is constant. You have phase, which vary 4 phases, and this can be we can write as a odd multiple of pi by 4 So these are the pi by 4. Now you can see it's 4 bits. So you have 4 different symbols. So you have 4 in the denominator. So we raise to the power of 4. So this 4 and 4 cancel. So all this symbol collapse to odd multiple of pi, and that is this position. So we lose all the information. We lose all the phase information and reach to this point by doing the power of 4. And if you have a phase error, so phase error is this phase and some added phase error terms. And if you take the power of 4 here, so this get cancel and this get go to the pi, and this goes m times phi t. So for example here, this is your original symbol. Because of the phase error it's move. Let's say it's a little bit moved. In practice it move a lot, but let's say a little bit move, and it moved to here because of the phase error. Now if you go to the power of 4, all this solid one collapse to here. This is the actual information, and all these error terms collapse m times phi k. So basically we find out this angle m times of the phase error, and then we just divide by m, so you get phi k. And then you do the angle information. Angle is e to power phi, so we need to do argument operation, and then you find the phi k. Now the problem lies here. So it's all the DSP, it's all the computation, it's all the processor which work on the current, and it do mathematical operation. Now, if you remember, if I try to find that phi k, so any angle, if you add two pi terms, it's the same angle, right? Any angle, if you add 2 pi, 6 pi, whatever you add and add, it represents the same angle. So when the computer do it, when the DSP do it, it doesn't know it's phi k or it 2 pi multiple of something. So we can represent it like n times pi, 2 pi. N is the natural number. So you can say that this is the, so actual the DSP doesn't recognize this m times phi k, it recognizes m times phi k plus some multiple of 2 pi. And if you divide by m, then it will be phi k plus 2 pi by m. So basically we add the DSP by virtue of this mathematical operation, uh, find your phase error, but also find some extra offset in this region, minus n pi to plus n pi. So for phase estimate, it's by divided by m. So this extra error, which is coming of the mathematical operation, is called phase ambiguity. So it doesn't find out correct phase error, but correct phase error plus extra terms. And if you try to compensate the phase error, so phase error goes away, but then it's added the extra phase term, which causes the rotation of the symbol. So let's say this is the QPSK. You estimated the phase error and apply that, and we compensate all the phase noise and everything. And because you compensate everything, but because this extra term, constant phase term present because of the DSP, so your symbol was, which was here, it can move here or here, or individual symbol can move here and here. This is only for n equal to 1. It can be n equal to 2, 3, and 4, something like that. N equal to 1, you don't get error because it's in the same quadrant. N equal to 2, you get some error. And so this is the something we can't avoid. This is going to be present because it's computational problem. It's a problem of the DSP. So only way to avoid it if you use the differential encoding and decoding, because differential encoding doesn't depend upon the absolute phase, it depends upon the relative phase. So even if there is a phase offset, the particular phase offset minus previous symbol phase offset get cancelled, and you don't have this error coming out. So differential encoding decoding is still preferable if we can, to reduce the bit error. So far it's good, and differential encoding can help you, but there is something called cycle sleep. And why it's happened cycle sleep is because at one time we can only process n number of symbol or n number of sample signals, and we need to go in the loop, take sample signal, convert to the parallel, go through all the operation, take another one. So when a computer work on certain sample, it can select certain value of n for phase ambiguity, and for the next cycle, we don't know which value of n can select. For example, let's say if here select n equal to 1, and here it select n equal to 2, so it's different phase ambiguity. Now, even if you use differential encoding, it so far is good in both cases, but when it reaches to the age one, because differential use the age one, so here this one minus this one phase the differential is going to use, and here is n equal to 2, here is n equal to 1. So your phase offset, which was constant in the differential encoding, is no longer constant. So it means it's varied by more than pi. So it basically pi or 2 pi in some terms. So this term of varying the phase because of change in the segmentation or change in segment of the sample we select, it causes the cycle sleep. And because of the cycle sleep, the phase which was in the same quadrant, it might go to other quadrant. And let's say the phase was here, it goes to this quadrant, we completely lose it. We have a bit error. So our symbol error, as you can see here. So how to remove the cycle slip? So they use something called segment change algorithm, which try to track what value of n computer choose for different segment, and if it is different, then it try to equalize. So basically, this is the segment change detector, which we try to check for every sample, every block of sample, what is the value of n computer change, and then it's increase or decrease to equalize the same value. Now, so once it find out the phase error, you multiply here. So let's say the actual one is 5k, and you found out phi I is estimated one, which may or may not be equal to 1 because the phase estimation is not never equal, never correct. So may not have the same phase estimation, but you apply the reverse of it. So you end up with this 5k minus phi e, which is lower than the actual phase error. So at least you have some lower phase error. Also, the sort noise is also reduced because you applied with this number. Now, if you have a larger block size, so the phase error the estimation will be very bad, because if you choose lower and lower, the symbol have correct error and you try to find out the correct phase error if lower number of sample. So if lower number of sample, actually you can get good phase error, but then sort noise not be good. If you have a longer phase sample, if you take longer sample, the processing power or processing time will be longer as well. But in that case, the phase error will be inaccurate, but the sort noise can be reduced. So there is always a kind of optimization what to choose. Okay, so okay, so in terms of so this is the so far what we use differential for the differential system. As we discussed, that differential always try to is better for the phase ambiguity. It can reduce it. But even for certain cases, it might not reverse. For example, the cycle slip. And if your signal is very highly distorted, sometimes the intensity level is very highly distorted. So they try to normalize, instead of detecting this, they try to normalize the intensity, so that if you normalize the intensity, everything reduced to nearby one. So this intensity variation will reduce. So phase estimation will be a little bit better. And that's the trick they play around when we have so much noisy signal coming into. Okay, now how we detect the square quam. So for a star quam is simple. Because intensity is symmetrical, the phase is symmetrical. So you take intensity information out, and the phase you can do phase recovery and do the phase. We discussed before how to recover the data from the phase from constellation. You apply the logic circuit for decision making. But for a square quam, you can see the phases are not symmetrical. You have different intensity level. So this is a square quam. You can see it look like a square. I drawn here as a circle, but it's actually a square one. And you can see it has three different level of intensity. So more than three different level of intensity, and phases are not symmetrical. So inner and outer circle has symmetrical phase, but the middle circle has no symmetrical phase. So how do they recover such signal is they choose different symbol, recognizing where are the where they lie on the constellation diagram. So for inner and outer circle, they choose certain symbols and then go to power 4, because like QPSK, you can say only 4 symbols. So go to the power 4 and follow the same procedure what happened before, and then you can recover the phase. For the middle one, then you choose another class of symbol for the middle one, which is 8 symbol, and they go to the power of 8 and follow the same procedure. They combine together and remove the phase error. So basically, they need to decide which class of symbol we have, class 1 and class 2, and we don't know, it's randomly coming, so we don't know. So they need to select a large number of sample for everyone to have enough symbols in class 1 and class 2 class 2 circles of the constellation diagram. And that's why you need to select the large block length to ensure that we have enough symbol from each class. Okay, this is another mechanism they use. I'm not going to discuss this here. It's basically the same thing. Instead of going feed forward, they go feed backward. So they take from D minus previous D sample and try to estimate the phase from D, and then feed to the next one, and they do the same process. Just it's not feed forward. It's like a phase. It's like a feed backward. So backward feeding. It's like a digital PLL in the sense. It's usually not used in general. Okay. So another frequency offset estimation. The frequency offset is this one. You remember delta omega, the phase frequency difference between the channel and the local oscillator itself. Although we don't need to do it separately because the digital phase estimation also estimate this as a combined part. If you remember, um, here this phi k also contain the frequency offset. But if your signal is very noisy, sometime we do the separate phase estimation, separate frequency offset estimation. And it's just some mathematical calculation. They go to the power fm, like for m symbols, and then go back to the delay symbol and take their transpose, multiply together. At the end, if you do this operation in the mathematics in the DSP, we able to estimate the delta omega term. Delta omega is the phase estimation, and then you they apply this minus of this term to the original sample, and so we able to reduce the frequency offset. This is the frequency offset estimation they use. And again, if you use phase estimation and frequency offset estimation both together, the chances of error will be lesser and lesser. So the corrected phase will be noted like this. Okay, so now I see some how the symbol look like when it passed through all the system at the receiver. So at the receiver end in optical domain, we receive this constellation. We transmitted 16 QAM, and here we don't find whether it's 16. We don't see anything which QAM it is at all. This is the optical domain we find. We put here, we pass through local oscillator, go through optical quadrature front end. After the balance detector, we have I and Q, the electrical domain signal, and then it go through all of this method we discussed, the reduction of dispersion and nonlinearity and so on. And then basically we are able to recover from here to here the some circular form. So we are get rid of most of the dispersion and nonlinear effect before the phase estimation. And because of the local oscillator, you remember we have delta omega term, the phase delta phi term, the phase noise term, and the fixed offset phase offset term. Because of those, it's coming of the phase local oscillator. We have all this present. So all this circle present because of this local oscillator. So they do phase estimation, not local oscillator, but also the residual dispersion and nonlinearity as well. So all of this causes this circular, and then they do phase estimation. And when they apply the phase estimation, they recover all these phase noises, which causes this rotation in intensity and phases, and then they recover this phase error correction. After phase error correction, they recover the original symbol. Sorry. Okay, now it goes to data recovery, and we discussed before as well how they did data recovery. So they are now you have a current which is free from the noises, and then they apply some data circuitry to decide whether the intensity is ranging from this range or that range, and apply the mathematics and say that it's bit 0 or bit 1 and so on. Similarly, they do for the phase. They try to decide which range it lies for the phase in the constellation, and then they try to do the same thing there. Okay, so to summarize for today, we discussed coherent detection, homodyne, heterodyne, and intradyne. We found that intradyne detection is preferable over all other the detection method. And so in the modern coherent receiver, we use intradyne detection. Now, depending upon the noise removal, it can be phase diversity and synchronous detection. The phase diversity was earlier version of in the commercial transceiver. Now we don't use it, so we go to the synchronous detection. And so synchronous detection is preferable because it has high sensitivity. It can demodulate absolute phase as well as it can demodulate the square form. Another thing we noticed that how it recover the phase, how it do basically the optical phase lock loop in the digital domain through the phase estimation. And it uses something called VNV algorithm. The mth power feed forward method is called VNV algorithm, Viterbi and Viterbi algorithm. So it uses this algorithm to remove the phase, or let's say it uses this to create a phase locking in the digital domain. Even it does all try to reduce the phase error, still because of the DSP, because of the mathematics in the DSP, because it's basically implement the mathematical function, there is cycle slip and phase ambiguity present, which can cause bit error. Even they try to use segment detection, but it's still sometimes it's present. So still it can cause bit error. So So overall, we have seen that how the optical signal is received, which is very noisy, and now we get back to the original constellation, and we go through a lot of DSP blocks to remove the dispersion, nonlinearity, and at the in the phase noises. And even we do all this thing, we can get to the correct, close to the correct symbol, but not actually correct symbol. And still, if you provide the decision circuitry, we can get bit error. So there are many sources of bit error, even in the DSP and even in the optical network, which can cause bit error. And the DSP try to minimize it, but it still is present. So how to minimize it? So they use something called forward error correction to even further reduce the bit error. So okay, so I think I would finish it for here, and I will organize the next section where I will discuss about the forward error correction and higher order modulation. If you have any question, you can ask now.
Abhishek, I had two questions. So
Yeah.
one was we have in Acacia, we have some settings for spectral pre-emphasis at the TX direction. So
Yeah.
how does that affect the filter design or recovery of the signal? That was one
Mhm.
question. Another question was we can change the optical sensitivity of the transceiver using power limited and noise limited mode.
Mhm.
So is there like, does that change the way local oscillator recovery is done, or how do we tweak the sensitivity of the receiver in these cases?
Okay, so the first one, you're asking the. Okay, so there I don't have the slides for that, but maybe in the next session I will add some slides, the DSP in the transceiver, and there you can see the basically what maybe I might have a slide. Let's see if I have something like that.
Yeah,
Basically,
spectral
they
shaping, I think.
yeah, like here you can see the spectral shaping. So basically, what happened when a signal is passing through a filter? Filter has limited bandwidth and sometimes is shifted from I2 grid, and because of that, it cut the side of the signal. Okay, most of the carrier clock synchronization and all this information lies here. So it cut the signal, and so we get bit error. So how they emphasize it? So basically, amplifier is going to reduce the power at the edge. So the best way to emphasize is to increase the power at the edge. So we call it bad signal. So the spectral pre-emphasis basically emphasize the edge at the spectrum in order that if it passes through the filter or any other in the network where it's going to decay, it will decrease down to the original level, and that's the spectral pre-emphasis. So that's why you get bad signal at the end. This is how it works. Maybe I will discuss next time how it affects the nonlinearity,
Sure.
how it affects the filter performance. Next time there are DSPs used in the transmitter as well. I discussed some of them there, but here I will discuss in more detail in next session. Okay. Okay. The sensitivity, how the I need to check the document of the Acacia, how they play around the sensitivity of the local oscillator. Okay, and I will get
Okay.
back to you. I need to think about it.
Okay. Because I think they have a noise sensitive mode and power sensitive mode. So for point to point links, we use the power mode, and noise mode is used in like amplifier and ROADM networks.
Okay,
So
so
that
one of the
s-
method, the DSP, I'm not talking about the Acacia DSP. I'm talking about in general DSP. One of the method they use for highly noisy signal is dividing by the intensity itself. So you reduce the basically you lose the intensity information temporarily to get rid of the intensity noise. So for highly noisy signal, this is the mechanism they use in DSP. Now coming, and that's how they try to improve the sensitivity of the receiver. But why I'm saying that I'm not sure about the Acacia, because Acacia don't reveal many information about the blocks inside, how which algorithm they implement, where because maybe trade secret for them or something. So they don't even reveal the information how they compensate the nonlinearity. They provide the function, user-defined function, but they don't reveal. So I actually don't know how they do it. But one of the
Mhm.
function is this to improve the sensitivity in the DSP. But I will check the document if they reveal something about it.
Okay. Sure. Sure. Thanks, Abhishek.
Yeah. Any other question? Okay, if not, then Chama, we can finish the session. And if people are interested, I can set up